Section 10.2 is all about triangles. A triangle is a geometric figure that has three sides. It also has three angles inside of it, or three interior angles as we call it. The most important rule about triangles when we're talking about the angles is that if you were to add up the three interior angles of any triangle, it will equal 180 degrees. So the sum of the measures of those three angles, again, of any triangle, is 180 degrees. We can classify triangles by their angles, and we can also classify triangles by their sides. Starting with their angles, if all of the angles inside a triangle are acute, it's also called an acute triangle. So if all the angles are smaller than 90 degrees, it's an acute triangle. However, if one of the angles is a 90-degree angle, we call this a right triangle. If one angle is obtuse, meaning more than 90 degrees but less than 180 degrees, then it's an obtuse triangle. Looking at the classification by sides, if two of the sides have the same exact length, it's an isosceles triangle. Notice that in addition to two sides being equal, the angles opposite of those sides are also equal in an isosceles triangle. Equilateral triangle means all the sides are the same exact length, and also every single angle is equal and measures 60 degrees. A scalene triangle is one where there are no two sides that are equal in length. So none of the sides are the same in a scalene triangle. Before we get started with the longer, harder pictures where they have you find in like 5, 6 missing angles, I do want to emphasize one of the big concepts here, which is, as I just mentioned in the last slide, if you add up any three angles of a triangle, it does equal 180. So let me go ahead and just draw a triangle shape. Please excuse my bad drawing skills as usual. Here we have a triangle. I'll just call it ABC. And I'm just going to pretend we have a 90-degree angle up here, clearly not drawn to scale. And let's just pretend angle B is 36 degrees. And let's say that it says find the missing angle. So I'm going to find angle C. If you have 2 out of the 3 angles like this of any triangle, you have enough information to find the third angle. So I have enough information to figure out the measure of angle C. We're working backwards, so we're going to subtract. We work backwards when we find missing angles. So we just said a minute ago that any triangle, all 3 angles, when you put them together, is 180 degrees. And you just take 180 to represent the triangle, and you subtract the 2 angles you have. So I'm going to minus the 90-degree angle, that's the box on the top, and I'm also going to subtract the 36-degree angle as well. So 180 minus 90 minus 36 means that we have a 54-degree angle for angle C. So in a minute, when we get to these bigger pictures and we have like 2 triangles and they say find like 5, 6 missing angles, you want to constantly check to see if you have 2 out of the 3 angles of any of those triangles, because if you do, you have enough information, as we've seen on this slide, to get the third angle. You just do 180 for the triangle and you just simply subtract the 2 angles that you do have of that triangle. There are going to be several homework questions where they give you a picture with a bunch of missing angles that they want you to find, like 5, 6 angles. There will be a couple of triangles inside these pictures as well. In order to get the correct answer for all the missing angles, we want to keep in mind 4 ideas that we've been talking about with these chapter videos. So I'm going to write look for. We're going to look for the following. So the first thing to look for is any type of a box shape, meaning a 90-degree angle. So if you see that box, that square, that's their way of letting you know that there is a 90-degree angle. They don't always have to label a 90-degree angle with a box, but if you do happen to see that box, that square shape, you want to immediately think 90 degrees. The second thing to keep in mind is, as we mentioned earlier in this video, any triangle shape, the 3 angles inside that triangle will always add to 180 degrees. The third idea is that vertical angles, those are the angles across from each other, are always equal in measure. So a lot of times you'll see some sort of an X type shape for that to happen. But those angles across from each other and any set of kind of X shape are always going to be equal. And then the fourth rule to keep in mind that we discussed in the last video, that was the section 10.1 video. This is the hard one. This is the one that's easy to forget about. Any straight line equals 180 degrees. So what'll happen a lot of times is you'll have one of 2 adjacent angles. You'll know what one out of the 2 angles equals. And as long as you notice, okay, I have 2 adjacent angles. I have this angle sitting beside another angle, the angle I want to find. Then they're supplementary angles, meaning they equal 180 degrees. So again, if you have 2 adjacent angles sitting on top of a straight line, and you know one out of the 2 of those angles, just keep in mind when you put the 2 angles together, they are supplementary. They do equal 180 degrees. So looking at example 1, it says find the measures of angles 1 through 5 in the figure shown. So as I'm looking at this figure, they've currently given us a couple of angles. I see a 58-degree angle here. I see a 36-degree angle here. And I see a box for 90 degrees way up here. Now, I cannot do anything with the triangles until I know 2 out of the 3 angles of the triangle. So, for example, if I look at this triangle here, I don't have enough information yet to figure out any of the angles. I only know 1 of the 3 angles. I know that the top angle is 58 degrees, but I don't know angle 3 or 4 yet. Again, I have to know 2 out of the 3 angles of a triangle in order to figure out the third angle. If I look at the other triangle down here, it's the same thing. I only know 1 out of the 3 angles is 36 degrees. So again, I do not have enough information to complete the other angles of the triangle yet. So I would recommend when you have a big picture like this, look at the triangles first. See if with either triangle you have 2 out of the 3 angles. If you do, that's where you would start at. Here, I don't have that information. So then I would look for any 90-degree angle, or any type of angle, honestly, beside any of the triangles. And the only other angle I'm given is this 90-degree box, this right angle right above that first triangle on the far left. Remember, the box means 90 degrees. So if I look closely, this 90-degree angle is supplementary with angle 1. So if you tilt this picture on its side, you would see that the 90-degree angle is adjacent to angle 1. So when I put these 2 angles together, they are supplementary in that they're sitting on top of a straight line, which is 180. So putting it all together, the measure, put little m for measure of angle 1 is 180 for the straight line minus its adjacent angle, which was 90. So 180 minus 90 means that angle 1 is 90 degrees. And I'm going to fill in the picture as we go along. It helps me to see it better. A lot of times what's kind of cool about these pictures is it's a domino effect. So now that I've seen what angle 1 is, it's 90 degrees, now I have enough information to get another angle. So now that I know that angle 1 is 90 degrees, I have 2 out of the 3 angles of that first triangle. So I have enough information to figure out angle 2. If I were to add up all the angles of any triangle, it equals 180 degrees. We are working backwards. Whenever we work backwards to find a missing angle, we do subtract. So I'm going to write 180 to represent that triangle minus 36 degrees minus angle 1, which was 90 degrees. So if you see a triangle and you have 2 out of the 3 angles, you do 180 degrees to represent the triangle, and you just simply subtract in any order the other 2 angles. So minus 36 minus 90. So when I do 180 minus 36 minus the 90 for angle 2, I get 54 degrees. And let's just erase some of these extra circles here. And I'll relabel the picture a little bit nicer. So angle 2, we just said is 54 degrees. And we said angle 1 was 90 degrees. And again, it's like a cool domino effect. So now, remember, angle 3 is across from angle 2, and vertical angles are equal. Angles across from each other are equal when you have that X shape. So if angle 2 is 54 degrees, guess what? Angle 3 must also be 54 degrees. So the measure of angle 3 is 54 degrees. And now that I know angle 3 is 54 degrees, I have 2 out of the 3 angles of the other triangle. So I have enough information to figure out the measure of angle 4. So I do 180 to represent the entire triangle, and I subtract the 2 angles I have in that triangle. So I would subtract the 54 degrees, and I would subtract the 58 degrees. So 180 minus 54 minus 58 means the measure of angle 4 is 68 degrees. Let me write this a little bit nicer. And we have 1 angle left is all to finish up the picture. A lot of times people get stuck here. Chances are, if you're getting stuck, you need to look for supplementary angles. Remember, supplementary angles equal 180 degrees. If you know the angle's adjacent angle, you have enough information to figure it out. So I know that what's adjacent to angle 5 was the 68 degree angle 4. We just figured that out. So to find the measure of angle 5, it's sitting on top of a straight line and it's adjacent to the 68 degree angle. Straight lines are 180, 180 minus its adjacent supplementary angle of 68 degrees. So I just simply do 180 minus the 68 degree angle beside it, that was angle 4. So if I do 180 minus the 68 degrees, I get 112 degrees for angle 5. I'll get rid of the label there. So again, angle 5 was adjacent to angle 4. They were supplementary angles. When you put them together, they're on top of a straight line. So I did 180 for the straight line minus angle 4, which was 68 degrees, and voila, we got 112 degrees for angle 5. I know these ones are a little bit harder, so let's try a similar example. I'm looking at example 2. Example 2 says find the measures of angles 1 through 5 in the figures shown. As we look closely, we have 3 angles. We have an 80 degree angle, a 40 degree angle, and a right angle for 90 degrees. I mentioned earlier that a good starting point is to look at your triangles first. See if they've given to you 2 out of the 3 angles of either triangle. And if not, then see if they've given you an angle beside either triangle. So here, if I look at the first triangle, I do not have enough information yet. I only have one of the three angles. I know that the top angle is 80 degrees, but I do not know angle 5 or 3 yet. However, if I look at the other triangle, I do have, yay, 2 out of the 3 angles. I have a 40-degree angle here, and I have a box for 90 degrees here. Because I have 2 out of the 3 angles, I have enough information to figure out the third angle inside that triangle, angle 1. So angle 1, the measure of angle 1 is 180 degrees to represent the triangle, minus the 90-degree angle, minus the 40-degree angle. So if I do 180 minus 90 minus 40, I get 50 degrees for angle 1. Because vertical angles across from each other are the same, I do have a weird X shape there with angles 1, 2, 3, 4. The angle right across from angle 1, that 50-degree angle, was angle 3. So the measure of angle 3 must also be 50 degrees. Because I know angle 3, I now have 2 out of the 3 angles of the other triangle, the triangle on the left. So the measure of angle 5, the third and final angle of that triangle, I do 180 to represent the triangle, minus 80, the 80-degree angle on the top, minus angle 3, which we just said is 50 degrees. I do 180 minus 80 minus 50, and I see the measure of angle 5 is 50 degrees. Let me erase a little bit and clean this up. But I did get 50 degrees for angle 5. So the only angles we have yet to find are angles 2 and 4. You can do either one next. I'm going to go for angle 2. Remember, if you get stuck, most likely you're going to look for supplementary angles. If I combine angle 2 with angle 3, yep, they are adjacent angles that are also supplementary. So the measure of angle 2, get a darker color here going. Let's go with the blue. The measure, there we go, of angle 2 is 180. They're on top of a straight line, minus its adjacent angle with angle 3, 50 degrees. If I do 180 minus 50, I get 130 degrees for the measure of angle 2. And finally, angle 4 is right across from angle 2. Those vertical angles across from each other are equal. So if angle 2 is 130, guess what? Angle 4 must also be 130 degrees. So just constantly be on the lookout for the 4 principles listed on the top of the screen. I do want to mention that the My Math Lab homework will have you type the answers in numerical order, even though you don't always find the answers in numerical order. What do I mean by that? So you would type in the measure of angle 1 first, which is 50 degrees. Then they'd have you type in the measure of angle 2, which was 130 degrees. Then they'd have you type in angle 3, angle 4, and finally angle 5. Example 3 says explain why the triangles are similar. So similar triangles are when all 3 angles are equal in measure. In other words, all 3 angles of the larger triangle are the same exact measurement as all 3 angles of the smaller triangle. Now, when the homework in My Math Lab asks you the same question, they don't explain it like that, unfortunately. They're going to summarize it as, these triangles are similar because 2 of the angles, so 2 of the angles of the larger triangle are equal in measure to two of the angles of the smaller triangle. So why do they just say two angles are the same? Well, if you think back to the beginning of this video, we talked about if you were to add up all three angles of any triangle in the world, it would equal 180 degrees. So if you know for sure that two angles are equal between two triangles, it implies that the third angle is also equal. So to be similar triangles, all three angles between the big and the small triangles are going to be equal in measure. But the homework is going to just mention two of the angles being equal because the third angle is also equal is implied when they phrase it that way. So if you look at our example here, you'll notice that the angles that are equal have the same number of tick marks in them. So angle A of the larger triangle is equal to angle D of the smaller triangle because they both have one tick mark in them. Angle C is equal to angle F. They both have two tick marks in them. And angle B equals angle E. They both have three tick marks in them. Now, when you have similar triangles, what's neat is that there is a proportion that will always help you to find a missing side of one of the triangles. You can use that proportion to figure out a missing side length. Looking at our example here, let's see if we can figure out what that proportion is. We're going to compare the corresponding similar sides. These are the sides that connect the same angles together. For example, side DF in the smaller triangle connects the one tick marked angle to the two tick marked angle. It's 3 inches in length. It must be similar to side AC of the larger triangle because that side also connects the same exact angles, the one tick mark to the two tick marked angle, and it's 6 inches. So once we figure out what the proportion is, it is going to be what you multiply by to go from the small to the big triangle. And it looks like to get from 3 inches to 6 inches, they must have a proportion of 2. They're timesing by 2. But let's double check all the sides just to make sure that that proportion seems correct. So it looks like the proportion is 2. Looking at another side, I'll change the color here to color code it. Side DE of the smaller triangle is 2 inches. It's similar to side AB of the larger, which is 4 inches because both of these sides connect the one tick marked angle to the 3 tick marked angle. And sure enough, it does look like the proportion is 2 because if you times by 2, if you take the 2 inches times 2, you get the 4-inch side of the larger triangle. And then finally, the third side, side EF of the smaller is 4 inches. It's similar to side BC of the larger, which is 8 inches. Yep, to go from 4 to 8, they must have multiplied by 2. So once you figure out what the proportion is, you just simply multiply all the sides of the smaller triangle by that proportion to get the length of the sides of the larger triangle. If you wanted to work backwards, you would just simply divide by that proportion. So, for example, I know the proportion here is 2, so if I wanted to go from the bigger triangle's dimensions to the smaller triangle's dimensions, I would just simply divide each side of the bigger triangle by 2. The problem is that your proportion is not always a nice whole number like 2. So sometimes you have these weird decimals or fractions that can be proportions. So there's a two-step procedure that will guarantee us a way to figure out a missing side when you're dealing with similar triangles. Example 4 says, find the missing length x. So as I'm looking at these two triangles, they're trying to trick us because the smaller triangle is completely flipped around and upside down when we compare it to the larger triangle there on the left. First, we need to figure out, are these similar triangles? Because if they are, there's going to be a two-step procedure to how to find a missing side with similar triangles in the homework. So if we can figure out at least two of the angles are equal between the smaller and larger triangles, that's how we're going to know that we are, in fact, dealing with similar triangles. So already, as I look at the two triangles, they both have a 90-degree angle. So that's one angle that they for sure have the same. As I look at those triangles, I also see an X shape in the middle, which means we have vertical angles or opposite angles. So these opposite angles that I'm using my red pen here to identify are equal. So I have one tick mark. I'll put in them just to show that they are equal. So there we go. There are two angles of the smaller triangle that are equal to two angles of the larger triangle. The vertical angles are equal and the 90-degree angles are equal. Because 2 out of the 3 angles are equal, that implies that the third angle must also be equal. So this angle up here on the smaller triangle, I'll use black pen and 2 tick marks, must be equal to this angle down here, 2 tick marks again, of the larger triangle. So now that I know, okay, these are definitely similar triangles, the angles are all equal, here is the two-step procedure you can use to figure out the missing side x. You don't have to do it this way, but I'm going to do the next two examples this way for consistency purposes. And that way you have a backup plan. If you're trying it another way and it just doesn't work, you can always use this two-step procedure to figure out the missing side. So step 1, you're going to have a fraction equal to another fraction every time you're dealing with similar triangles. So I drew fraction bar equals fraction bar. And there are so many different ways you could set up these fractions. The way I'm going to do it is I'm going to put the smaller triangle's side on the top of each fraction divided by, and I'm going to put the bigger triangle's similar side below it. So let's see what I'm talking about here. So to begin, pick any side of the smaller triangle. So I'll just pick the 12-inch side. I could do 12 or 15, either one. It really doesn't matter which. So I'll start with the 12-inch side. And then you want to put the similar side, that's the side that connects the same exact angles together, of the big triangle right below it, so it belongs to the same exact fraction. So be careful here because these triangles are all flipped around in weird ways. So you're looking for the side that connects the 90-degree angle to the 2 tick marked angle. So that is actually going to be side X. It also connects the 90-degree angle to the 2 tick marked angle. So 12 of the smaller triangle divided by its similar side x of the bigger triangle equals, let's go ahead and do that with the other sides we're given with the other fraction. So back to the smaller triangle on top, 15 inches. So 15-inch side over which side of the bigger triangle is similar to the 15-inch side? Well, the 15-inch side of the smaller triangle connected the 90-degree angle to the vertical angle with the 1 tick mark in it. It's similar to the 20-inch side, which also connects the vertical angle to the 90-degree angle. Again, that's just one way, several ways you can set up these fractions. Once you have that done. That's the hard part, is step 1. Step 2, now whenever you have a fraction equal to another fraction, we are allowed to cross multiply. So when you cross multiply, thinking back to your last algebra course, bring down the equal symbol. It's still in the middle. And the word cross, because you're going to picture a cross like an X shape. And you're going to multiply the numbers and letters on the diagonal there. So whichever diagonal you want to begin with, that's fine. I like to begin with whichever diagonal has the letter, the variable in it. So I'm going to do x times 15 first, or 15x. So 15 times x, when I multiply the first diagonal together, equals, on the other diagonal, I have 12 times 20. I'll use parentheses for times. 12 times 20. So I now have 15x equals 12 times 20 gives me 240. Last step, to solve for x, you want to divide the 15 to the other side to get x by itself. I'm using fraction bar for division. So x equals 240 divided by 15. When you divide that out, that gives you 16. The units are the same as the original picture, which are inches. So 16 inches is the final answer for x. Let's do another one of these. I know they're tricky, but it's going to be the same 2 steps once you get the hang of it. Again, you do not have to do it that way. If you're like, hey, I just figured out the proportion, and then I multiplied the similar side of the smaller triangle by that to get x, that works too. However you want to do it, you should be getting 16 at the end of example 4 there. Looking at example 5, it says find the height of the lookout tower shown in the figure using the figure that lines up the top of the tower with the top of a stick that is 2 yards long and 3.5 yards from the line to the top of the tower. And they did give us a picture as well, which helps. However, I know this slide here, the picture is extra small. So before I begin, I'm going to draw these triangles a little bit bigger just to see them better. Please excuse my lacking artistic ability. But I see 2 triangles, a big triangle and a small triangle. So the big triangle has the lookout tower, which they're calling H, on the left side. The entire bottom of the bigger triangle is 56 yards, according to the picture. And then if you look really closely, here's the smaller triangle inside. The left side of the smaller triangle, that's the top of the stick, which is 2 yards long. And then the bottom of the smaller triangle is really hard to see. So if you look at the original question, that was the 3.5. So from here to here, that was the 3.5 yards. In fact, let me erase that and write this a little bit better. So bottom of the smaller was 3.5 yards. Bottom of the entire big triangle was the 56 yards. There we go. All right, so whenever you have a triangle inside of another triangle and both triangles are standing on the ground, you can assume they are similar triangles. Why do I say that? Because you can assume that both of these objects, people, whatever they mention in the word problems, are perpendicular to the ground. So that's a 90-degree angle right there that they have in common. They also are sharing this angle on the far right in common. And as soon as you see 2 angles that are the same between the bigger and smaller triangles, you now know officially you are dealing with similar triangles. What is nice about example 5 is at least the triangles are drawn in the same direction. They're not all like flipped upside down like in example 4. So it's going to be easier to see and identify the similar sides when that happens. So here we go. Example 5, step 1. Jotting that down, step 1. Okay, so we said step 1, you're going to have a fraction equal to another fraction, and I'm going to set it up like I had in example 4, where I'm going to put the smaller triangles dimensions on the top of these fractions and the bigger triangles information on the bottom. So starting with the smaller triangle, pick either side of the smaller triangle to begin. So I'll just go with the 3.5 side. So 3.5, and then the similar side of the big triangle needs to go right below it on the fraction. So this was the bottom of the smaller triangle. The similar side, since the triangles are drawn in the same direction, is also going to be the bottom of the bigger, which is 56. Now going over to the other fraction, the other side of the smaller triangle they gave to us anyway was the 2-yard side. That was the left side. And its similar side of the bigger triangle was h. So that's the hard part, is just getting those fractions set up. So now step 2, we're ready to do the algebra part, the cross multiplying. Bring down the equal symbol, it's in the middle. I'm going to multiply the diagonal, which has the letter first, so that's going to be 3.5 times h. The other diagonal is 2 times 56. When you do 2 times 56, you get 112. Remember, you're multiplying what's on the diagonals. Now, last step, to get h by itself, divide the 3.5 to the other side. Running out of room here on the slide, I apologize. But you're going to do 112 divided by 3.5. Let me rewrite that a little nicer. So 112, fraction bar for division, 3.5. And when you do that, you should be getting 32. The units of the original picture were yards, so that's going to be the units of the answer. It's not always a nice whole number, so just be careful. Usually if it's a decimal, they'll have you round to the nearest 10th spot, but they will specify if it is a decimal. The homework will tell you how far they want you to round it. But 32 yards, final answer for example 5. The Pythagorean theorem tells us how to find the third side of a right triangle. So this famous formula only works on right triangles. Those are triangles with a 90-degree angle in them. The formula that I'm sure everybody remembers is a squared plus b squared equals c squared. However, be very, very careful with this formula because it does have an important restriction. That restriction is the letter c, that's squared by itself, has to represent the hypotenuse side. So you can't just plug in whatever sides you want into this formula. So if I take a look at the picture of the right triangle inside that Pythagorean theorem box, I can see that sides A and B represent the legs. The legs are the two sides that come together to form that 90-degree right angle. The hypotenuse, which they call C, is the slanted side across from the 90-degree angle. Now, why do they use letter C and not H? Well, we're going to see in a later video that H represents height with various shapes. So the letter H was already taken for something totally different. So they chose C instead to represent the hypotenuse side. So all this fancy formula is doing is showing us a relationship for every single right triangle. It's saying take one of the legs, which they call A, and square it, raise it to the second power. Plus, take the other leg, which they call B, and square that as well. and it will always equal the hypotenuse, which they call c squared. Notice every single side is squared in this formula. Let's take a look at a couple of examples. One example will solve for hypotenuse, and the other example will solve for a leg. Example 6 says to use the Pythagorean theorem to find the missing length in the right triangle. Use your calculator to find square roots, rounding if necessary to the nearest tenth. So as I look at this triangle, they've given us two sides, an 8-meter side. Remember, little m stands for meter. And they give us a 15-meter side as well. It is a right triangle, so I can use the Pythagorean theorem to find the third side, which they're calling C. So the first step, once you know it's a right triangle and you have two of the sides already, is to go ahead and jot down the formula. So I'm going to write a squared plus b squared equals c squared. Now let's go ahead and plug into the formula. Either leg is fine to plug into A, so I'm just going to call the 8 side A. Remember, the legs are the two sides that come together to form the 90-degree angle. So 8 gets plugged into A, it needs to be squared, plus the other leg we'll call B is 15. So 15 gets plugged into B, it's also squared, equals the hypotenuse, that's the slanted side across from the 90-degree angle. They're calling it C, and it also needs to be squared. After you plug into the Pythagorean formula, next step is to take all the numbers and square them. It's up to you if you want to do it in your head or use a calculator. We need to do 8 squared, which really means 8 times itself. We also need to do 15 squared, or 15 times 15. Even though these might be easier numbers that you already have memorized what their squares give, I'm going to go ahead and bring the graphing calculator onto the screen just to show you where the exponent button is located at for the harder numbers you need to square that you're going to see in the homework. So a couple different ways you can do squared in the graphing calculator. The way I'm going to do 8 squared is I'll type in the 8 first, and then here's your exponent button right here. It's the up arrow, the caret, right above the division button. So I'm going to use the up arrow, and then I type in the 2 exponent. The cursor is floating in the air, so I'm going to hit the right arrow key to bring the cursor back down to the ground, and then I press enter down here for equals. It's on the bottom right corner, and there's 64. And then I'm going to do 15 squared, so that's 15. Again, up arrow for exponent. The exponent's a 2. Use the right arrow key to bring the cursor back down. I hit enter, and that's 225 because it's 15 times 15. So jotting down those answers, we said 8 squared gave us 64. Bring down the plus symbol in the middle, we haven't touched yet. We said 15 squared was 225. Bring down the equals and the c squared. Now the numbers 64 plus 225 are on the same side of the equation, so let's go ahead and combine them, add them up. 64 plus 225 is 289. Bring down the equals and the c squared. Once the letter squared is solved by itself, which is what we have here, we have c squared by itself equals 289. The last step is to figure out just what c is. In other words, get rid of the square exponent. The opposite of a square is a square root. So I'm going to go ahead and do the square root to get rid of the square, but I got to square root the other side of the equation to keep it balanced. So the hypotenuse c is the square root of 289. Remember, square root means what times itself gives you back the 289 that's underneath it. Button. So if you look for the number 7, go up and left from that, and the square root is above x squared. So just think you're going to color code to get square root onto the main screen. Mine is blue. Yours might be a different color. That's okay. But you're going to have to hit 2 buttons to get the square root on there. You're going to hit second, which is right here. Hit second. As soon as you hit the second button, an arrow appears in the cursor, and then you're going to hit x squared. And you'll know if you've done it correctly because the square root should come onto the main screen. If it does not, you can always hit clear and try again. So if I clear it out, again I hit second, followed by x squared. Then I'm going to type in the 289. Then I hit enter for equals. And 17 is the square root of 289. So jotting that down, C, the hypotenuse, equals 17. We keep the units the same as the original picture. The original picture had little m's for meters. So 17 meters is the final answer. If I had gotten a decimal instead of a nice whole number, remember they would want me to round it to the nearest 10th spot, which is 1 digit past the decimal point. Let's try another one that's a little bit harder, where we have to solve for a leg instead of hypotenuse. Example 7, use the Pythagorean theorem to find the missing length in the right triangle. Use your calculator to find square roots, rounding if necessary to the nearest tenth. So yet again, we have a right triangle. We know 2 out of the 3 sides, so that all means we can use the Pythagorean theorem. So step 1, let's jot the formula down. A squared plus b squared equals c squared. So we're solving for a leg is what's different about this example. So we have one leg, which they call A, so just leave A as A, and it needs to be squared, plus the other leg here is 16. It also needs to be squared when you plug it into the formula, equals C, the hypotenuse, which is the slanted side across from the 90-degree angle, is 20. So 20 goes into C to be squared. We kind of go ahead and divide away, rope off the triangle there so we can see the formula a little bit better. I currently have A squared plus 16 squared equals 20 squared. Once you plug into the formula, next do all the numbers squared. So just bring down the A squared and the plus symbol. We're not touching it yet. We're going to do 16 squared, which is 16 times 16. You should be getting 256 when you do this calculation. Bring down the equal symbol. Now let's do 20 squared, or 20 times 20, and you should get 400 when you do that. Before we can solve for A, we first need to get A squared by itself, which means I need to move the plus 256 to the other side. When you want to move a number to the other side, thinking back to algebra, you've got to do the opposite operation. The opposite of plus is obviously minus. So I got to do minus 256 to boot it to the other side of the equation. So bring down the A squared you haven't touched yet, and bring down the equal symbol. We're going to do 400 minus 256, which gives us 144. Once you have the letter squared by itself, then at the very end, you can do square root to get rid of the square. I'm also going to square root the other side. So A is the square root of 144, which is 12. The units are the same as the original picture, which were centimeters. So we should be getting 12 centimeters as the final answer. Now we're not always going to get these nice whole numbers. When you do get a decimal, they do want you to round to the nearest tenth, which is 1 digit past the decimal point.